Today we will talk about elimination reactions. As you may recall from our previous discussion on substitution reactions, if you have a substrate mixed with another substance, in this case a nucleophile, you end up doing your substitution reaction. But if the nucleophile happens to have basic properties, so if you have a moderately to strong base as your nucleophile, something else can happen. And specifically, if you actually use heating for carrying out the reaction, the separate pathway by which this can take place is a reaction in which an alkene gets created. Specifically, the nucleophile reacts as a base, the substrate reacts as an acid. Simply put, the nucleophile removes a proton from the substrate, and the proton that is removed has its electrons move over and kick out the leaving group. So in the process you form an alkene, you form a protonated nucleophile, basically the conjugate acid of the nucleophile, which in this case is just the base, and a salt. So you have a number of byproducts in this thing. So here the only thing we're really changing from our original criteria is that the nucleophile is now really a base, so we're now referring it as a base. And you form your conjugate acids, the alkene, and your salt byproduct in the process. Now, if you consider the substitution reaction, you have two reactants and you end up forming two products. Therefore, the entropy of this reaction is relatively constant. It's not really changing all that much because you have the same number of molecules on both sides of the equation. But when you look at an elimination reaction, you start with two reactants, but you end up making three products. And what this means is that the entropy in this reaction is actually greater than zero. You do increase the number of molecules as you go from reactants to products. And as you may remember from general chemistry, the delta G is equal to delta H minus T delta S. Assuming that delta H is relatively constant in these two reactions, then automatically the entropy is going to dictate what happens. And of course, if you increase the temperature more and more and more, the negative T delta S term will dominate delta G. And that will make the process be more spontaneous. So when you're carrying reactions, specifically if your nucleophile is a moderately basic substance, if you want an elimination to happen, you want to increase the temperature. On the other hand, if what you want is a substitution to happen, you want to keep the temperature down as much as possible, probably not go much farther than maybe 30 degrees Celsius. So just remember that the temperature is going to favor elimination, whereas low temperature is going to favor substitution. Okay, so with that definition established, the second thing we need to do is revisit the nomenclature of alkenes, because now we're going to look at alkenes that have more than two groups bound to them. And so we need to distinguish what is trans and what's cis in such outcomes. In the past, as I just mentioned, the alkene could have up to two different groups bound to it. And if the groups were pointing away from each other, you had your trans configuration. If they were pointing in the same direction, you had your cis configuration. But what happens when you have more than two groups bound to the same alkene? How do you end up naming the molecules, and how do you determine whether it is the cis configuration or the trans configuration? Well, there's a set of rules that we're going to follow in order to determine the names of these molecules. So let's start with the molecule on the left. The first thing that you really want to do is you want to focus on the carbons of the alkene specifically. And once you do that, you really want to focus on the actual things that are bound to that specific carbon. So we're going to separate this alkene into the two halves. So you have the half right here, to which the chlorine and the bromine is connected. And then we have the other half of the alkene in which we have the methyl and the hydrogen connected to the same carbon. So basically we're just going to compare the two groups that are bound to the same carbon, and we do that for each side of the alkene. And technically speaking, what I mean by comparing is that we are going to use the same rules of prioritizing groups as we did for stereoisomers. So we're gonna once again utilize the Kahn-Ingold-Prelog rules. And you do this per side of the alkene, right? So I don't want you to compare, at least not at this point, the groups across the alkene. It's only the groups that are bound to the same carbon. So in this case, you compare chlorine to bromine. The priorities, if you remember, are based on the higher atomic weight first. Between chlorine and bromine, bromine has the higher atomic weight, so that has higher priority. Between carbon and hydrogen, carbon has greater atomic weight, so carbon has priority. So once you determine the priorities on each one of the subsets of this alkene, you simply determine the cis or trans isomerism by looking at how the highest priorities arrange in respect to each other. But there's one addendum to this. Instead of calling the molecule cis, you're going to refer to it with a Z uh, prefix. And instead of using the word trans, you're going to refer to the molecule with the with the letter E as a prefix. So in this case, since the bromo group and the methyl group, which are the highest priority groups on each side of the alkene, are opposite of each other, we're going to use the E prefix. And notice that we are using parentheses the same way we did for the R and S configurations of stereoisomers. And that precedes the entire name of the molecule. So this is your 1-bromo, 1-chloro, 1-propene. Okay, let's look at the second molecule in our series. Same thing as before. We want to focus entirely on just one carbon of the alkene and the groups that are bound to that specific carbon. So this carbon over here has ethyl bound to it, and it has methyl. This carbon over here has isopropyl, and it has methyl bound to it. So in terms of priorities, you simply need to look at how much hydrogen content each one of these carbons has. This is a CH2, whereas this is a CH3. CH2 takes priority over CH3. Over here you have a CH, and down here you have a CH3. CH takes priority over CH3. So you got your two priorities pointing in the same direction. This is a cis configuration, so we're going to use a Z prefix. And in terms of naming, you can count the longest chain, which is 1, 2, 3, 4, 5, 6. So this is a hexene molecule. Specifically, we have 1, 2, and 3 methyl groups sticking out of it. So this is the 3Z configuration, because that's the point where the alkene first appeared. And notice that we're using also 3 to name the alkene itself. So 3-hexene and 3Z at the very beginning of the name of the molecule. And of course 2,3,4-trimethyl to tell where the methyl groups are sticking out of the molecule. Okay, and we have one more. For this molecule, same idea. You break it into the two halves. The one half of the alkene containing its substituents, and the other half of the alkene containing its own substituents. The priorities are based on higher atomic weight first. So if we look at the oxygen versus bromine, bromine has greater atomic weight. If we look at the carbon and compare it to the oxygen, oxygen has greater atomic weight. So once again, we have groups pointing in the same direction. So this is the Z configuration. And this molecule, the longest chain has 1, 2, 3 carbons. So this is propene once again. And the groups right here, these are your methoxys. Alright, so one methyl present connected to oxygen, and the oxygen is also connected to the parent chain. This is your methoxy, or alkoxy substituent. And you happen to have two of them, two alkoxys. So we're going to first start by naming the configuration 1Z. Then we have to introduce the bromo group, followed by the methoxy, right? And don't forget to use the numbers to tell where the methoxy groups are located. And of course, one propene. Okay, so with that, the last thing to mention in relation to the alkenes is their overall um, strength and stability. When we discuss infrared spectroscopy, we will talk about the energy that it takes to vibrate the bonds. And generally speaking, the higher the energy, and all these numbers right here are in inverse centimeters, which is directly related to energy, the higher these numbers become, the more energy you have to put in to vibrate the bond. And in essence, what that implies is that the bonds are stronger. So when you look at these bonds, you can see at the monosubstituted alkene, disubstituted alkenes, which has three categories: vinylidene, cis, trans, trisubstituted alkenes, and tetrasubstituted alkenes. You see an increase in the actual energy required to stretch those bonds. And there's an explanation for this. Pretty much what you're seeing is that the more substitution there is on the alkene, the more stable the alkene is going to be. Now, when you compare trans, cis, and this is called your vinylidene alkene or geminal alkene, you can look at the homo-LUMO interactions, specifically the LUMO of this CH bond in relation to the HOMO of that adjacent CH bond. And you can see that in the trans configuration you have the best overlap. These orbitals are not only parallel to each other, but the biggest lobes of the LUMO are next to the HOMO. Whereas in the cis configuration you have somewhat offset bonds that are not exactly parallel to each other, and on top of that, the smaller regions of the LUMO are the ones that are closest to the HOMO, so that's not a great interaction. And on the vinylic configuration of your disubstituted alkene, you have almost orthogonal interaction, so you have very little interaction going on there. So what you can see here is just based on this homo-LUMO argument, you would predict that the carbon-carbon double bond will be the strongest for the transalkene, followed by the cis, and having the weakest one for the geminal configurations. Okay, so this just tells us a little bit about the bonds, and in due time we're going to talk a little bit more about what it means to have a stronger bond from the point of view of spectroscopy. So when you compare these alkenes, and by the way, these are all isomers of each other. They have the same number of carbons, and they all have the same number of double bonds. It's the only difference is that the double bond is located at different places in the alkene. You have different configurations like the cis versus the trans or the geminal, or you have different amounts of substituents bound to the alkene. So this is what we call the monosubstituted alkene, only one thing attached to the CC double bond. The pink molecule, which is the cis configuration, the trans configuration, and the vinylic configuration, they both have two things bound to the carbon-carbon double bond, so we call those disubstituted. The green one down here has three alkyls or three groups bound to the CC double bond, so this is trisubstituted. And the last one has four things bound to it, which is tetrasubstituted. But regardless, all of them have the same number of carbons. So what we're looking at here is the combustion. We start with any of these molecules, we react with oxygen, we form carbon dioxide and water. And in each one of these cases, we're going to form the same amount of carbon dioxide and the same amount of water. So the products, in terms of energy, are going to always land on the same place. The thing that's going to differ is where the reactants appear in the energy profile. And ultimately, it's the position of the reactants that's going to dictate how much heat we're going to get out of this reaction. The higher in energy the reactants are located, the more energy we're going to get from this process. And the lower the reactants are located in energy, the less energy we're going to get out of this process. So in essence, less energies of combustion imply that the reactants were more stable to begin with. Higher energies of combustion are going to imply that the reactants were at higher energies and were less stable. Okay, so what we end up finding out is that the lesser the substitution on the alkene is, the less stable the molecule tends to be. And within the disubstituted case, generally speaking, what we see is that the cis alkene is less stable than the trans alkene. And interestingly enough, and this is still kind of open up for discussion, the geminal seems to have, by just looking at the combustion of this reaction, seems to be a little bit more stable than the trans alkene. So in essence, if you look at the graph again of the transition state, um, the energies of the reactants will be as follows. We have the monosubstituted higher in energy, followed by the disubstituted, first by the cis, then by the trans, then by the vinylic alkenes. And after that, at the very bottom, we have the trisubstituted, and of course the tetrasubstituted at the very bottom. And so that's how we get lesser and lesser and lesser and lesser and lesser energy of combustions, right? Because we start with a more stable alkene. And technically speaking, this stability trend, the fact that the more substituted alkene is, the more stable the alkene tends to be, is what we call Zeitzev's rule. Alkenes of higher substitution are thermodynamically more stable. And I'm going to try to explain relatively briefly why this is. If you consider the HOMO of an alkene, we're talking about the carbon-carbon bond, which is technically a pi bond. The LUMO, on the other hand, is an empty p orbital that's combined with, and these are, by the way, hydrogens, so these are s orbitals. And notice that the s orbitals are of opposite phase to the p orbital. So this has got a little bit of an anti-bonding character to it, but it is the first orbital available that it's empty. And so this is the LUMO. So what happens is that when you bring this fragment, which corresponds to one of the substituents here, so it could be a CH3, in this case it's technically CH3, and combine it with a pi orbital, well, the interaction of this p orbital with that pi orbital can lead to a bonding interaction, which lowers the energy of this orbital. And of course, if the p orbital right here is of opposite phase to the pi bond, you get an anti-bonding interaction. But the orbital up here doesn't have any electrons. It's the LUMO of the system. This orbital has 2 electrons, so this interaction alone of the substituent bound to the alkene to the HOMO of the alkene ends up lowering the energy. So you can see that having more of those groups present on the alkene is going to lower the energy more and more and more, and that stabilizes it. So that explains why having more having more substituents on the alkene tends to lower the energy of the alkene and make it more stable. The part that is more difficult to explain is that of the disubstituted alkenes. And I'm going to make a very far-fetched attempt at trying to explain this, because by looking at the infrared spectroscopy, we would have predicted that this was perhaps the weakest one, the vinylic case. And based on the combustion trend, it seems to be the one with higher energy. So let's find out why this is, or try at least to explain it. Maybe a little bit unsuccessfully. So we're going to compare the trans to the vinylic or geminal alkene. And I'm going to use a website known as WebMO that allows you to calculate energies to some decent amount of accuracy. Now, what I basically do in terms of calculations is I look at the molecular orbitals, all the way from the HOMO, the highest occupied molecular orbital, down to the lowest energy orbital, which in this case is 11 orbitals below the HOMO. And I simply write down the energies associated with them for the geminal configuration and the trans isomer. And if you add up all these energies, it tells you roughly how much energy you have for the molecule. And even in this setup, we find out that the geminal and the trans alkenes are very close in energy. So I wouldn't necessarily call the geminal a more stable configuration. It doesn't really help too much, but just to give you an idea, how this website works. These are the molecular orbitals that you tend to see. So this is kind of my attempt at trying to explain that stability trend. But truth be told, you'd be better off just memorizing the trends, because even I don't have a great explanation as to why this happens. With this one, I kind of show you that it's a little bit more stable, the geminal, than the trans from the molecular orbital calculations, but it's not, at least to me, it's not very convincing. Considering the errors associated with this program and this calculation, a difference of 2 kilojoules is not particularly convincing. Okay, now in the next video, I'm going to start talking to you about the two kinds of elimination reactions, and we'll continue going forward in terms of talking about factors that favor one reaction over the other. So see you in the next video.